What up, everybody? I'm the math teacher Goat, and this is a full lesson on AP Precalculus 1.3 rates of change in linear and quadratic functions. Now, if you've seen my other videos, you'll know that I'm giving you a full lesson. If you go to the description, you will find a PDF where you can download the notes, print them out, put them on an iPad, whatever works for you, and you can follow along. This is exactly what I would teach to my own students if I were teaching them. In fact, I will be teaching them this exact same lesson. So please please subscribe. You guys subscribing just goes a long way for me, and it helps my channel grow a little bit more. So please do that. It don't cost you nothing. It don't cost you nothing. So let's just get right into it, please and thanks. All right. Let's zoom up. I always like to start up with a warm-up that seems to make sense for everything. In this lesson, we are going to start out by using the slope formula to find the slope of a line connecting those points right there. Now, there's our good old friend, the slope formula. We know it. We love it. I always like to label my points x sub 1, y sub 1, x sub 2, y sub 2, so that when I plug it in, everything's already there. So y sub 2, I labeled negative 11, minus y sub 1, I labeled 3, so let's fill that in over there, over x sub 2, which I labeled negative 8, minus x sub 1, which I labeled negative 4. All right, negative 11 minus 3, very straightforward, negative 14, don't need to overthink it. We got a double negative here, so negative 8 plus positive 4 is going to be negative 4. Negative over negative is a positive. 14 over 4, those are both divisible by 2 7/2. See? Easy peasy. Wasn't that fun? So much fun. Today we are focusing on a lot of rate of change, and rate of change is a fancy word for slope, so we'll probably deal with this guy or something that looks exactly like it in the near future. But we're talking about things that are linear and quadratic. We're going to hit both of them. Both of these. So, first thing that we're going to talk about is a function is blank if the rate of change of the rate of change is the same over consecutive equal length input value intervals. This is an absolutely terrible phrase that you will see on multiple choice questions all the time. Consecutive equal length input value intervals. I can't even get it right. What does that mean? Input is the x. So if you notice, all of these go up by 1 every single time. So that would mean consecutive equal length input value intervals. The fact that each of these go up by 1 every single time makes that the case. Now, this guy over here, it's talking about the rate of change of the rate of change. Well, the first rate of change is if I were to go over this and say, all right, well, it looks like what we're doing is we're subtracting 5 to get from 7 to 2. To get from 2 to negative 1, we're subtracting 3. And then to get from negative 1 to negative 2, we're subtracting 1. And then now we're adding 1. And then now we're adding 3. And then now we're adding 5. These aren't the same. Now you might know that if your rate of change is the same exact number the whole time throughout, that gives you a linear function. Well, this is not linear because this is not the same exact constant number all the way throughout. So, if we're going to talk about just the rate of change being the same, that would be linear. However, I care about the rate of change of the rate of change, which means I'm going to do this. And to get from negative 5 to negative 3, I add 2. And to get from negative 3 to negative 1, I add 2. And from negative 1 to 1, I add 2. And from 1 to 3, add 2. And from 3 to 5, add 2. So the rate of change of the rate of change is now the same. And if the single rate of change is going to be linear, well, wouldn't it make sense that the next guy is going to be quadratic? And so, yeah, it would make sense. So we're just going to say quadratic. Okay, a function is quadratic if the rate of change is exactly the same number constant. And that's what we have here. We're going to do this quite a bit today. And we're going to be given the question quite a bit is this linear? Is this table linear, or is this table quadratic? And the way we determine if it's linear is make sure these guys go up by the same number. And if these guys go up by the same number, it's linear. And if it's not, then you go to the next one, which makes it quadratic if they are. And if you're thinking, would that mean the next one's cubic? You're absolutely right. Stop talking like that. You sound ridiculous. Average rate of change, slope of a secant line. Now, a secant line, what the frick is that, you're thinking? Well, a secant line is any line that crosses a curve more than once. Okay, so if I put a dot here and call that dot A, it's going to line up with f of A as my output. If I put a dot here and call you B, it's going to line up with f of B, somewhere over there. Okay, now, the average rate of change is a perfect straight line slope connecting those 2 points. Okay, so the average rate of change over the closed interval AB, so that would be A to B, is the slope of the secant line from the point. So the average rate of change from here to here is literally just the slope. Okay, now I don't know what this picture represents, but right now, I'm going from decreasing to increasing. Well, that doesn't really matter. If I were to, back my car up for 2 seconds and go -5 miles an hour and then all of a sudden gun it for 12 seconds forward, I'm going to have a positive rate of change. And that's kind of what's going on here. And so what we're going to use is the average rate of change formula. F of B minus F of A over B minus A. Now, where do I get that from? That's the same as the slope formula that we saw up here, where I would call you x sub 1, y sub 1, and I'd call you x sub 2, y sub 2, and then I would do y sub 2 minus y sub 1, f of b minus f of a, over x sub 2 minus x sub 1, b minus a, and then I get my brand new, pretty new picture thing, formula. All right? So we're going to use that formula to answer this very, very, very basic question. Find the average rate of change between the points 5, -1 and -6, 2. So I'm going to do very similar to what I did with the warm-up, but I'm going to call you A and F of A, and I'm going to call you B and F of B. So my average rate of change is going to be me using this formula right here. F of B minus f of a over b minus a. I called f of b 2 minus I called f of a -1 over b I called -6 minus a I called 5. So we got ourselves a double negative, so I got 2 plus 3 going on, or 2 plus 1 rather, which is 3. Sorry, Freudian slip. -6 minus regular old 5 is going to be -11, so this becomes -3 over 11. Ugh, terrible band. So my average rate of change between these 2 points is the slope connecting those 2 points, which is -3 over 11. So the average rate of change is the slope connecting the 2 points, if we haven't made that clear quite yet. All right, so average rate of change is the slope, average rate of change is the slope, average rate of change is the slope. Find the average rate of change of each. Well, this is slope-intercept form, isn't it? Isn't this in the form y equals mx plus b? Average rate of change is the slope. U, the number in front of x when y is all by itself, is my slope. So my average rate of change is -3 over 2 because the average rate of change is the slope. You're also linear. So this graph is very straightforward. It's a positive slope. I'm going to go up 1 over 1, 2. So my average rate of change over here is just positive 1/2. Easy peasy. Now we have another average rate of change question, but we only care about stuff that happens on the interval 1, 2. Now let's see, this is a piecewise function that lives here below -3. This is between -3 and 0. Ooh, this is where I want it. This 1, 2 lives in between 0 and 3. So I want the average rate of change of that part of the piecewise function. And that part of the piecewise function right there is basically the equation y equals -2x plus 3. And last time I checked, that's slope-intercept form. which means my slope is the number in front of x when it's linear and y is all by itself. Therefore, the average rate of change of u is going to be the slope, which is -2. Now, you were linear, you were linear, you were piecewise, but the area that I seem to care about is linear. When are we going to talk about the quadratic stuff, you were thinking? Mr. Goat, when are we going to talk about that? Well, let's do it together, shall we? Now, we're going to view this from a graphical point of view. Okay, we're going to try to look at the graph and really understand what we said towards the very beginning with the whole definition of what it means to be the average rate of change of the average rate of change. All right, now let's find the average rate of change of these 1, 2, 3, 4, 5 intervals. Okay, and these intervals are going to be given to us as 1 unit at a time. We go from -2 to -1, then -1 to 0, and so forth. No skipping, no jumping, no hopping, no, I don't know, I can't think of any other thing. Get your thesaurus out. -2 to -1. Okay, well, -2 lives here, so right there. -1 lives here, so right there. Oh gosh, why did I pick such an ugly looking graph? And it looks to me that my slope right here between -2 to -1 is going to be down 2.5 over 1. So this is going to be down 2.5 over 1. So -2.5, I'll write it out as -5 over 2. Okay, or -2.5, who really cares? Okay, now to go from -1 to 0, okay, here's -1, here's 0. I'm going to go down 1/2 and another 1, so down 1.5 over 1. So down 1.5 is -3 over 2, or just, -1.5. Let's go from 0 to 1. So from 0 to 1, looks like we're only going down 1/2 over 1, so that is -1/2. Or -0.5. Okay. Now we're going from 1 to 2. So from 1 to 2, we're now going up 1/2 over 1. So this is going to be +1/2, or just 0.5. And last but not least, we're going from 2 to 3, right? So that's up 1.5 over 1. So that's going to be up 1.5, which is 3 over 2, or 1.5. Now notice, this is just the rate of change. Okay, this is just the rate of change of the numbers. Okay, now the average rate of change, this is kind of what we're getting at. I'm not doing this for funsies. We're kind of approaching something right here. So let me scroll up just a little bit. The average rate of change for a quadratic function does not stay the same. And you can see that the average rate of change went from -2.5 to -1.5 to -1/2 to 1/2 to 1.5. So that did not happen here. For consecutive equal length input value intervals, so again, as these went up by 1 every single time, the average rate of change of the average rates of change of a quadratic function is constant. Now, I didn't show you that yet. Now, we saw it already in a table. But notice this is just the rate of change. If I were to look at the rate of change of these rates of change, these go up by 1 every single time. So this is the regular rate of change, and this is the rate of change of the rate of change. So for this case, that constant number is a +1. Okay, so this is quadratic, and we can see it. It's a parabola. This is quadratic, but we can also calculate it by taking the average rate of change over intervals of 1 and taking the average rate of change of the rates of change. And since the rate of change of the rate of change is a +1, constant number, it's quadratic. We're happy. Everybody wins. That is how you do it. Okay? So just, time to really get into some examples now. Time to get into some problems, the types of problems that you would see on your homework and stuff like that. Find the average rate of change of the function 3x squared minus 2x minus 4 on -3, 1. All right, so we're given an interval. Okay, I'll call you A, I'll call you B. I need to find the average rate of change, which is f of B minus f of A over B minus A. Well, here's the thing. I have b and I have a, but I don't have f of b and I don't have f of a. So I'm going to have to calculate that by plugging stuff in. So f of b is going to be f of 1, which means I take u and I replace every x with 1. So 3 times 1 squared minus 2 times 1 minus 4. Okay. 3 times 1 squared is going to be 3 times 1, so you become 3. 2 times 1 is 2, minus 4. 3 minus 2 is 1. 1 minus 4 is negative 3. So f of b is negative 3. F of a is the same thing as f of negative 3. So that's going to be 3 times negative 3 squared minus 2 times negative 3 minus 4. Negative 3 squared is 9. 3 times 9 is 27. Okay. Minus 2 times negative 3 is going to be positive 6 minus 4. So we have 33 minus 4 gives us an awkward 29. Oh, my age in a few years. All right. Where are we? So I have f of b. Okay, so f of b I just found out is negative 3. So negative 3 minus f of a I just found out is 29. All over b minus a, which is 1 minus negative 3. So I got negative 3 minus regular 29. Negative 3 minus 29 is 26. What is that? 1 minus negative 3 is 4. So those are both even, divisible by 2. Let me write it over here where I just have a teensy bit more space. 26 over 4 is 13 over 2. All right. Not pretty, but it ain't gotta be. You know what I'm saying? All right. More. For consecutive equal length input value intervals, if the rate of change of the average rates of change of a quadratic function is positive. Okay, now this is new. If the rate of change is positive, that means the graph is concave up at that moment. For consecutive equal length input value intervals, if the rate of change of the average rates of change of the quadratic is negative, then the graph is concave down. Now, if the rate of change is positive, it's increasing. If the rate of change is positive, it's concave up. So if the linear says positive, increasing. If the quadratic says positive, concave up. If the regular rate of change, linear, says negative, it's decreasing. But if the rate of change, quadratic, is negative, it's concave down. So if we take a look at this guy here, first we notice that x's are all going up by 5, so we have that equal length input value interval thing going on. Okay, we notice that you go down by 25, you go down by 35, you go down by, wait a minute, did I screw that up? You go down by 25, you go down by 25 again? Oh, it's 35. I didn't do anything wrong. What's wrong with me? You go down by 40. You go down by 50. So it's not linear. And here's the thing. It's not quadratic either. So when we have a case like this, I was hoping that maybe this would be one of those problems where we can see where this is linear or quadratic. But this is neither linear nor quadratic because you change. So if I wanted to do a problem like this and ask you the question, is this linear or quadratic? It's neither because these numbers aren't the same. No number is constant. So I was hoping that this problem would be like, where is it concave up or concave down? That isn't even an option because it's neither linear nor quadratic. So this type of problem is not linear or it's not quadratic either. Probably should have asked you what type of problem this is ahead of time. Bad job by me making notes. Still like and subscribe though, please, I beg you. The value of a function g, values rather, of a function g is given as selected x value table below. The function is either concave up or concave down, but not both. Determine if it's concave up or concave down. I should have put that up there. All right, so you go up by 1 every time. The x values go up by 1 every time. You go up by 2, you don't move. You go down by 2, and you go down by 4. Now this is linear. Linear has nothing to do with concave up or concave down. I need to find the quadratic values, the rate of change or the rate of change. It looks like you go down by 2, you go down by 2, you go down by 2. So since the rate of change is negative, since the rate of change of the rate of change is negative, we are looking at concave down. Okay? Determine if each table is linear, quadratic, or neither. If it's quadratic, is it concave up or concave down? Really should have given myself a little bit more space here, but that's all right. Let's zoom in though. Didn't mean to do that. Let's zoom in though so I can like really focus on every problem. All right, I need to find out if you're linear or quadratic. Okay, so let's make our little L. You go up by 1 every time, so we're safe. You go down by 2, you don't move. You go up by 2, you go up by 4, you go up by 6, you go up by 8. So you are not linear. So let's check to see if it's quadratic. You go down by 2, you go up 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 by 2, and you go up by 2, which means you are quadratic. Now the second question is, if it is quadratic, is it concave up or concave down? Since the rate of change is positive, it's concave up. Okay? Let's do it again with you. All right. Let's get a different color. You go up by 2 every time, so we got that equal length. You go down by 4. You go up by 4. You go up by 12. You go up by 20. So it's not linear. It's a quadratic. You go up by 8. You go up by 8. You go up by 8. So it is quadratic. Is it concave up or concave down? Since the rates of change are positive, this is concave up again. Very creative job by me coming up with problems that I stole from the internet. Let's see about this guy. Linear, quadratic, or neither. All right. You go up by 1 every time. You go down by 3. You go down by 3. You go down by 3. You go... oh no, I take it back. You go up by 3. Wait. You go down 3. You go down 3. You go up 3. And you go up 3. Okay, so it's not linear. Is it quadratic? You don't move. You go up 6, and you don't move. So this is neither. Okay? Not bad. Last page. Bunch of examples. These are the types of problems you should expect to see on homeworks and test questions and yada, yada, yada. The table gives values of the function h for selected values of x. If the function is linear, what is the value of h of 15? Well, if this is linear, then why don't I just do slope-intercept form stuff? And why don't I do not even slope-intercept form, let's do point-slope form. I haven't done point-slope form in a while. Okay, so this is what I'm going to do. I'm going to label you A. By the way, choosing these points means absolutely nothing. F of A, F of B. I'm picking 2 points, right? Now, this is going to give me my slope. My slope is the rate of change, so my slope is F of B minus F of A over B minus A. So in this case, my slope is going to be F of B, which is 5, minus F of A, which is 17, over B, which is 4, minus a, which is negative 4. So I've got 5 minus 17 is negative 12 over 4 minus negative 4 is 8. Those are both divisible by 4, so we're left with 3 halves. Now I'm going to use point slope form, which is y minus y sub 1 equals m times the quantity x minus x sub 1. Okay, so why don't I, since I already used these 2 points, why don't I just use u as my x sub 1, why not, and u as my y sub 1. So plugging all of this in, I have y minus 23 equals my new slope, 3 halves, times the quantity x minus negative 8 or x plus 8. Now what they want us to do is find out h of 15, which means I replace x with 15. All right, hopefully I have enough space for this. Y minus 23 equals negative 3 halves, 15 plus 8. So y minus 23 equals negative 3 halves. 15 plus 8 is 23. Ugh. All right, so this is not going to be pretty at all. That's all right. Let's move it up here because I'm completely out of space. Y minus 23 equals, let me see, 3 times 23 will be, 69. It's going to be negative 69 over 2. Oh boy. I'm going to add 23 to both sides. Now, since this is over 2, I'm going to turn 23 into something over 2, and that's going to be 46 over 2. So I'm going to add 46 over 2. I'm sure you saw what I did there, AP Precalculus students. Okay, negative 69 plus 46 is going to be negative 23. That's going to be over 2. So there you have it. Okay? Okay. A couple more. The table gives values of function g for selected values of x. If g is quadratic, what is g of 8? I'm going to approach this differently. I'm going to make life a lot easier, okay, than the last one. This is what I'm going to do, okay? I have goes from 0 to 2, 2 to 4. I'm going to pretend that you're a 6, and I'm going to pretend that you're an 8. So what I'm going to do is I'm going to add and build on this table. I'm just approaching things differently than I did with the last problem, because why not? And we're going to fill stuff in. This is quadratic, which means the same quadratic number, the same rate of change of rates of change number is constant. Okay, right now, you go down by 4. Actually, you go up by 4. And you go up by 1. So that's my linear. Which means my quadratic change is going to have me going down by 3. Now, I need to build the rest of this. Okay, I need to build the rest of this, and we're going to kind of create some puzzles. I already know that you're going to be negative 3 and you're going to be negative 3. So 4 minus 3 is 1. 1 minus 3 is negative 2. Negative 2 minus 3 is negative 5. See what I did? Negative 5 plus 4 is negative 1. Negative 1 plus 1 is 0. 0 minus 2 is negative 2. Negative 2 minus 5 is negative 7. So, at 8, I'm at negative 7. Isn't that clever? Aren't we all smart? Yes, the answer is yes. This problem is an absolute god-awful nightmare. I hate it, but there's a homework problem very similar to this, so I kind of want to do it. So the function p is given by p of x equals g of x plus 1 minus g of x. So you have g of x, I don't know what g of x is, but g of x plus 1 minus g of x is going to be p of x. Then it tells us that p of x is 2. So this is saying that whatever g of x is, if you add 1 to g of x, you will always get 2. The difference between these guys is always going to be 2. Okay, now, what does that mean? Let's look at our options. Okay, let's look at our options. We have 3 possibilities here. Possibilities number 1 mentions p is positive and constant. Okay, so let's see if this is true. All right, now, this statement is not true. While g is increasing, its slope might not always be positive. Now, by doing this, okay, by saying g of x plus 1 minus g of x equals 2, it tells us that the difference between them is always 2, which means it's always increasing, okay? So 1 states that it always has to be a positive slope. I don't know if that's the case. I don't know if that's the case. While it is increasing, its slope might not always be positive. It could be a step function. It could be a piecewise function. It could be something that, I don't know, is none of those. So I can't say 1 is true. 2 says, because p is positive and constant, the graph g is concave up. We said nothing about anything being quadratic, did we? And since we said nothing about anything being quadratic, we can't prove that it's concave up. However, here we are at 3. And 3, we can say that this is increasing because the difference between the two is a positive 2, therefore is increasing. So the only possible answer that makes sense here is going to be 3. This is a very difficult problem to understand. It's a very challenging problem. But again, what you're doing is you're comparing this function with that function. By adding 1, you're getting something that's also positive. So up 1, or over 1, up 2, you're looking at a positive slope. Again, it's just a very difficult, very bizarre problem. But hey, we did it. We did an okay job. So get that out of the way. All right, that does it. Make sure you like and subscribe. Now that you're done these, please go to my AP Precalculus random videos. All you have to do is AP Precalc and just type out 1.3 and you will see a bunch of problems. So again, now that you're done this, type out like Math Teacher Goat Precalculus or AP Precalculus 1.3 and you will get videos that look like this, and it'll be types of problems that you could see about what we just did. But that's the end of this video. Again, like, subscribe, watch my other videos, tell all of your friends about it. Again, subscribing isn't that hard. Just hit that little button and it makes my life a whole lot easier. I would really appreciate it. Thanks for watching. Bye.